Hello. Good morning, good evening, good afternoon, depending on where you are in the world. This is Greg Risterman from Olympus. I'd like to welcome everyone today to this webinar introducing WeldSight software for the Focux PX phased array system. WeldSight software combined with the Focux PX system provides a logical, streamlined workflow for repetitive high production phased array weld inspections in many applications, such as wind towers, API tanks, ASME piping vessels, and friction stir welding of aerospace materials. In this webinar, you'll get an overview of WeldSight software and see how it streamlines your workflow for inspection engineering, setup, calibration, acquisition, and weld flaw analysis. Our presenter today is Chris Magruder. Chris has worked at Olympus for 18 plus years, providing customer training and application development for advanced phased array, time of flight diffraction, and ultrasonic testing inspections. This informational webinar has been scheduled for approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of the screen during the presentation. If we're not able to get to your questions during the live webinar, they will be addressed personally, either by email or phone after the event. Now, without further ado, I'd like to turn the presentation over to Chris. Chris, take it away.
Hello, everybody. Thanks for joining us. I saw a lot of familiar names in the sign-up list, and we have a big group today. Our objectives for today's webinar are an explanation of the WeldSight software and its benefits for weld inspection. We're going to do an overview and demonstration of the Eclipse Scientific Beam Tool integration in WeldSight for the management of probes, wedges, components, and scan plans. We're going to do an overview and demonstration of the software workflow in WeldSight, including scan plan integration, beam set creation, beam UT configuration, calibration, and preparation for data acquisition. There will be a follow-up webinar to this for analysis and advanced acquisition techniques. We're also going to do an overview and explanation of some typical WeldSight software applications. WeldSight and the Focux PX is a weld inspection factory specialist, and API 620 LNG tanks, ISO wind tower inspection, friction stir weld, ASME piping and vessels are just a few of the applications. What is WeldSight? WeldSight is Olympus's acquisition and analysis software for the Focux PX phased array instrument. The Focux PX is a industrial phased array instrument with a 32-128 PR pulsar configuration and supports phased array TOFT and UT inspections. WeldSight is also the successor to TomoView for OmniScan X3 support. The software expedites upfront engineering, operator training, and data acquisition for advanced PA, UT, and TOFT inspections of welded components. The demonstration we're going to see today is going to start in the UI, and we will be in the ES Beam tool for the scan plan creation, just to review some basics regarding the integration in WeldSight. The beam set creation in WeldSight, either as a single beam set or an entire configuration. Overview of the user interface. We are going to set up and calibrate phased array beam sets and the TOFT beam set, and talk about the data acquisition overview, all of which include some new features for Olympus. I'm going to go ahead and transition to my computer desktop, where we'll be looking live inside the software. Everything in WeldSight starts with the ES Beam tool for the beam set creation. WeldSight has a very simple workflow divided between setup, calibration, inspection, and analysis. The software header updates appropriately for the various beam types of phased array TOFT or UT. In the example I have here, in a single ES Beam tool file, we have all of Olympus's most common New Weld series probes for the DLA, DMA models, A31, A32, Pipe Wizard probe, common TOFT, and UT models. Prior to use in WeldSight, we can take any single beam set that's been pre-configured and realize it in the software by replacing the current beam set or adding to the existing configuration. The ES Beam Tool installation is detected by WeldSight and does not require any unique consideration. It can be run outside or inside the software, and we're going to use several of the ES Beam Tools files for the various components between the beam set management, calibration blocks, and pieces. Prior to getting started in WeldSight, we're going to review quickly a few ES Beam Tool basics. The demonstration we're going to see today is a 2-phased array probe, 1 Toft inspection of a typical weld component. And there's a few parts of this that we're going to use in WeldSight that you might not have had to configure otherwise. So to realize this configuration from a new configuration, we're going to start with the component piece and the weld. The piece and the weld make up these two forms, and we will import our component that we select from a library of pre-configured inspections. The EBP file is the piece and weld overlay file that we'll use in WeldSight to update inspection to inspection. We've imported the component file, and we'll also take the calibration block. In every ES Beam Tool file, there is a default calibration block that doesn't include any targets. The Beam Tool has a very useful calibration block generator, and we're going to pull from a library of pre-configured calibration blocks. In this example, is very typical of ISO compliance with wind towers that uses a series of side drilled holes and notches for the TCG sensitivity, for the time of flight validation, for the ID and OD notches for inspection coverage. But in today's example, we're going to use a typical ASME vessel type block with a series of side drilled holes. The ES Beam Tools calibration block designer makes configuration of blocks, both piping and rectangular, for side drilled holes and notches from any orientation or position, very simple and fast without having to be a CAD operator. So back to the piece and cal block that we've already configured. To realize our probe sets, we're going to import these from a toolbox of Olympus's common models. We will take phased array beam set 1, phased array beam set 2, for which the only difference is a mirror. In the beam tool, we must configure the instrument ID for the Focux PX, of which 4 daisy chains together are possible, and the start channel of the pulsar. This 65 represents the position of element 1 on the second probe on the 128 element multiplexer of the Focux PX. Another way to realize probe sets is directly from the probe menu. If we select one of the 4 probe types, it will place a default, and we can just replace this with our particular model. In this case, a 10 megahertz Panametrics 563 Toft with an N60L wedge. So just like that, we're back to our complete configuration of probe, wedge, scan plan, beam sets, component, and calibration block. And again, the BTPS file, Beam Tool Probe Set, is where we manage the probe, wedge, and beam sets that can be modified in WeldSight. So in WeldSight, we'll load the file for our demonstration that includes the complete EBWK scan plan, probe, wedge, beam sets, component piece, and calibration block. And in one click, we'll realize with the load all, in one click, we'll realize the 3 beam sets in our WeldSight configuration. Upon generating the beam sets, the beam tool form closes, and I realize the beam sets here. We want to give them a name that makes sense. Skew 90, A32 probe, aperture 28 elements, focus projection 20 millimeters. And we have the two-phase array and the top beam set. The active beam is always displayed in the header with the active beam set. Some of our displays are designed so that they will follow the active beam set or fixed displays for acquisition. The piece menu is where we visualize the component that we just imported with the scan plan and the calibration block and material velocities. This manages the skip overlays that we see on the S-scan. The A-scan overlay that you see here is available, and it defines the has entry to our inspection area and the has exit from our inspection area, and updates with the active beam set and beam. At any time, a shortcut key available to update the new component overlay in piece without disrupting our beam sets or calibrations, which is very typical in the windmill inspection, wind tower inspections, and in the LNG tank inspections and repetitive factory inspections. The display layouts that you see are available from a predefined list that comes with the installer and are customizable. Under the display layouts that we see here, to realize a new configuration, we split vertically or horizontally. We'll select our setup layouts for an S-scan, A-scan, and B-scan, scale the windows appropriately, save, and this configuration can be moved up or down and need not be in the order of which they were created. And again, most of our layouts are designed between a setup configuration and calibration, an inspection layout, and then post-analysis layouts as well. The dashboard that you see here, similar to TomoView, can be displayed or hidden, and it includes our inspection start and pause, a series of icons. This is a focus beam set on the SA sound path distance in gate A, auto 80 amplitude for the active beam set range on cursors, and range and the cursor management for hiding. These icons are related to the flaw table that we'll learn about in this next webinar for advanced analysis. The readouts for WeldSight, the trigonometry and cursor readouts, use OmniScan nomenclature. They're divided between a gate A red, gate B green, and the weld gate from the has zone defined in the ES beam tool. Customizable lists are available for phased array, conventional, UT, and TOFT, and further subdivided for cursors, gates, sizing, and zone. Display layouts or the customizable readings can be saved as an independent layer and added at any time to analysis. For our full data file and setup file, we save all of the various layers under the same extension, including the complete ES beam tool file, and they can be, again, loaded only for the display layouts or the customizable lists for the phased array. The Focux PX, when used with WeldSight, enables a 400% amplitude saturation. We display 100% amplitude in the A scans and 200% amplitude in all of the calibration menus. There are shortcuts throughout the software. If I double click on any UT axis, I get the UT settings. Double click on the scan in the footer and I get the motion settings. Acquisition rate enables the digitizer. The instrument connectivity is available here. All of these menus are available from the header, but contain shortcuts throughout the software to minimize clicks and navigation. After we initially create our beam set, we have the ability to update between the cow block and the component in the footer. By selecting the cow block, I see the cow block overlays for the side, end, and top views. If we align the targets on the calibration block on multiple depths, we'll put a cursor at the depth position, and if I manipulate the probe to see the extremities of the S-scan high angles and low angles while maintaining a consistent and parallel depth between the targets, what I have validated is that the wedge velocity, the height of the elements in the wedge, the exit points at the wedge interface, the component material, velocity, and the refracted angle have all been validated in accordance with any of the various codes. At this point, the only thing that I could improve on would be a correction of a wedge that was physically worn. Our workflow continues to the UT settings. The UT settings, again, are very typical of OmniScan or TomoView nomenclature. This is where we manage the reference and scan gain and soft gain. The UT mode, the UT axis is available in depth, path, or time. The pulsar was set when we imported the beam tool configuration. The pulse width is set automatically based on the frequency of the probe, and we'll select appropriate smoothing and a filter for the frequency of the probe as desired. The position information from the ES beam tool shows us the probe and the wedge model and enables us to change the mechanical offsets for the scan and index or the beam skew. These are mechanical properties that must be changed in the field on the fly, and they do not affect our calibration or the beam delays and can be changed at any time. The rest of the information you see related to the piece is fixed and would only be changed by importing the EBP file or from bringing in a new configuration from the ES beam tool. The transmit receive tab is tabular information relating to all of the individual beams in the beam set. We can see the beam delays for every element. We can see the individual elements, and they can be deactivated when known to be bad. And it also includes all of the element delay and beam offset and element aperture information related to the beam and beam sets in the active beam set of the header. The digitizer is where we balance the speed of the inspection with the quality of the A-scan file size and S-scan imaging. When we import the beam tool configuration, we have a series of defaults and preferences that save us clicks in our configuration. In the digitizer, it's divided between the time base and then the real-time rates that we monitor during the inspection. A 100 megahertz digitization of a 5 megahertz probe with a compression factor of 10 generates a 0.15 millimeter resolution on the UT axis that is consistent regardless of if I change the range. If I change the range, the points adapt, but the waveform integrity and image is consistent. We display all of the resolutions in sound path, time, and depth for each of the beams, and we display the calculated half wavelength distance, which is a rule of thumb for a minimum detectable flaw based on the probe frequency. The interleave options we see here will scramble the order of the firing of beam sets and beams to minimize or move undesirable PRF noise, mostly associated with the calibration block. The rates that we see here are monitored real time. During the inspection, we can tune the A-scan, or prior to the inspection, we tune the A-scan to the speed of the rollers, whether that's the maximum roller of a wind tower fabricator or whether it's the maximum speed of the inspection, we can see this here during the inspection and monitor it real time. The software calculates the bottlenecks for the inspection, of which there are 4. One bottleneck is mechanical. The speed at which we can stabilize the probes and couple them properly is not displayed. The other 3 are related to the electronics and to the velocity of the ultrasound. What we know now is that our bottleneck is 73 hertz. I can move the scanner 73 millimeters per inch without 73 millimeters per second without losing data. And I know that my digitization time is the bottleneck. Going from an OmniScan inspection to a Focux PX inspection generally transfers the bottleneck for speed from the data transfer or the network cable to the digitization time. This would also enable me to improve on my A scans and S scan imaging by lowering the sound path resolution if desired. The digitizer again, can be opened and shut directly from the footer with a shortcut here. The gates are all digital. I can change the gates at any time before, during, or after the inspection. We get 2 detection gates from the beam tool, from the beam tool import. If in the beam tool the gate type and gate position are configured, we will realize these on importing the scan plan, and they need not be changed for calibration. The calibration functions use an independent gate. So once our detection gates are in position for the inspection, they need not be adjusted again. The TCG manager under the setup is where we're going to load and modify TCGs, but not where we create them. We'll create them in the calibration workflow that we'll see in a few moments. Before we move to calibration, we will go ahead and take a look at our TOF beam set. The workflow for configuring the TOF is to auto set the UT range on cursors. The UT settings adapt for conventional UT probes and TOF beam sets, different from the phased array. We will select an appropriate filter for the probe frequency, a TOF factor of typically 4 or 8. We will place 1 cursor on the back wall, 1 cursor on the lateral wave, calibration, TOF. We have a TOF configuration, TOF calibration tool for PCS wedge delay, and velocity. So prior to inspection on the cal block, we will update the wedge delay and stored in UT properties and the PCS and save those values for use on the component inspection for a 1-point wedge delay update of the lateral wave. We can see that the screen now is linearized. Red cursor at 0, the lateral wave, blue cursor at the back wall, and we can now take measurements. We'll update again this with a 1-point wedge delay in analysis mode on the component where a defect exists. Moving on to the calibration functions, the software adapts to the PA beam set and gives us a series of icons for the various calibration tools, of which several are normally required, normally not all of them. The first one is the acoustic wedge validation of the beam set that's active. What the software is doing now is creating a single element step, single element aperture E-scan across the entire probe for the probe connected on pulsar 1. It set a gate 5 millimeters before element first and several millimeters after element last and is comparing the height of element first and last to the design of the wedge. When the design is within the user-defined tolerance of 0.5 millimeters, in this case, we get a red bar. The software uses these two values and this slope to also calculate the angle of the wedge. So we have validated that it is the design that we selected is installed on the probe, and the design is not significantly worn to where it would require some update. We have a dedicated A-scan for this form to do any troubleshooting, and we can also, if the delays are out of tolerance because of real wedge wear, we can update the beam delays to the new value and save the beam set. This is required for every probe and every wedge that's installed on the configuration. This is a function that we would typically had done manually in the OmniScan or a TomoView previously, and now this tool just gives us a simple one-click version of that with some added and more accurate measurements. A similar function exists for testing the pulsars of the Focux PX, the probe elements, and the cables and connectors related to the splitters and the accessories. A similar configuration is realized, and the software is monitoring all of the pulsars in the instrument, for which any of them dead, we would see a white line and no main bang. We're monitoring all of the elements of the probe, and we can see that the total number of elements are inactive. Of the 64 are 12, which makes up 18.8%. 12 of those elements have an element next to it that's inactive, and there's some user-defined values and tolerances here. This is an area of the software that we'll see develop for linearity checks and for some of the probe checks that you would get with a new probe from the Olympus probe shop. The delay, time of flight, the sensitivity auto, sensitivity manual, and TCG functions need to reproduce everything we did in OmniScan and TomoView inspections, and the intent was that it would do it faster with better instrument specifications and fewer clicks. One example of that is the single point sensitivity check, typical of OmniScan. On a single target, we'll adjust the gate over our area of interest. All of the calibration windows that we see have a 200% screen height and the green target zone here in dB. But again, we avoid saturation up to 400%. We will take this to the end. While in any of the calibration functions, we have the soft state busy, and we will update a fast refresh rate and real-time A-scan display with the full 12-bit amplitude resolution. There's no more negative limitation for a correction in amplitude from any signal under 400% amplitude. Okay, select the calibration. This is a very similar function that we had always performed. Returning the software, exposing the probe to all of the beam sets within the tolerance zone, we get a green indicator status. The manual sensitivity is a new feature that is advancement or is a development from the 2- and 3-point inspection calibration of the OmniScan. In this case, we're going to set either a depth or a path gate over all of the targets from a static position on the inspection index offset. We'll select a number of targets. In this case, we'll select 5, and we'll add those targets. 1, 2. They can be done in any order. When the number of targets is achieved, the software will create a slope between the targets, and selecting calibrate will equalize all of the targets to 80%. This is a tool that we would use in parallel with the TCG. We would import a TCG typically, and we would account for the day-to-day serial number or coupling or minor differences in sensitivity for our daily inspection with this tool. Anytime we're in one of the sensitivity calibrators, the software is looking for another beam set that is eligible to receive this same calibration. And being eligible, it would have the same number of beams and the same basic beam configuration, which is typically a mirror. The TCG functions are probably one of the biggest improvements that solves an industry-wide problem in compliance with the acceptance criteria for amplitude inspections. How we create the TCG, the process, the workflow, and the software tools that allow the full dynamic range of the probe with current specs. So in this case, we're going to enable the TCG. We want all targets to be 80%. I'll select the number of targets up to 12 simultaneously that we want to calibrate. And in our example today, we'll use 7. We want all of the tolerances to be 1 dB. This calibration block is using a depth type design, so the gate is available in the depth or sound path as selected here. This is a digital TCG on the instrument, and we'll enter the smoothing points here that linearize the different detections at 5. So we're going to prepare to calibrate. I have 7 TCG points set. So the software is going to give me 7 independent windows. Each of the window is a 200% amplitude visualization with a 1 dB tolerance at 80% as set in our preferences. The first thing we're going to do is just take a quick peek and scan the cal block so we know the positions of the targets. The 7 gates are available based on the 7 points that I asked for prior to preparing the TCG. We'll place a gate over each target. 6, 5, 4, 3. When the gates are in place, I'm going to drive the probe all the way to the edge of the calibration block, clear the envelope, and maintain a consistent pressure and coupling as we scan the entire block. For any of the beams or points that do not have sufficient range to be exposed to all of the beams, they will be treated as being cropped manually. On any TCG point, we can limit the range of the TCG point, both on the end or the beginning of the S-scan for that particular point. After all of the windows are created, and the windows can be updated before or after we scan the block, we're going to select Calibrate TCG Points one time to apply all of the TCG points simultaneously. envelope. We'll rescan the cal block with the correction. And again, there's no negative limitation anymore for a TCG point. They can be positive or negative within the 400% amplitude. After scanning the block, we have a 7-point TCG, typical of ISO, ASME, API type compliance. We can copy that directly to another beam set, and we typically export the TCG for use in the future or on another mirror beam set. A TCG is a probe model and configuration, a wedge model, the S-scan beam set and resolution, the aperture, focus type, focus length, and the size of side drill hole or notch, and velocity. If you break one of those, the TCG is no longer valid. So saving and recalling the TCGs and then updating them for the day-to-day coupling probe serial number using either the sensitivity or the manual inspection is a preferred method for repeatability and compliance. I could have done the first 3 points, flipped the block over, and achieved the other points, or I could have done them one at a time in succession. In this case, I have a TCG block that supports doing 7 or even up to 12 points in a single pass. The velocity tool exists for validating phased array or for measuring new materials of an unknown velocity, and it's very simple. For the phased array check, just to do a quick velocity check, we would enable the cursors, and we would put one cursor at a fixed position of known depth or sound path. We'll change the data cursor to another fixed position or known depth, measure velocity, and the software will do a comparison between the velocity we used to create the beam sets and how we measured it, or in a conventional UT probe, achieve a new velocity for use in our scan plan. There is no correction for angle error or velocity. The only thing you can do is rebuild the beam set, beam or law file with the correct velocity. Wedge delay fixes are designed to manage a worn wedge. They are not designed to manage a bad velocity. Typically, we wouldn't use a different velocity for every inspection. We would use a fixed velocity for known materials, especially carbon steel or stainless steel. After the calibrations are complete and we've gone through the full workflow of the setup and calibration for phased array, we would typically set our scan inspection sensitivity reference gain here at 19.1 dB. Our inspection reference sensitivity is set, and this number becomes scan gain. Prior to inspection, this is a hardware gain. After inspection in analysis mode, that's a software gain, and it's blind to the users. The readings, such as the ABDR, will always show us the signal gate A amplitude relative to the original reference sensitivity, irregardless of how much soft gain or scan gain we use during the inspection. So we see here our ADBR reading, typical of ISO compliance in the wind tower industry, doesn't change. It's only reflected from the 19 original dB. the window, the visible A scan, and the gate data here will change with that resolution. So after we have set our inspection, setup and calibration, the workflow continues in the inspection. Under the motion control settings, WeldSight is capable of single encoder line scans, 2 encoder raster scans, or no encoder clock scans, typical of probe in hand development and testing in a lab. This form is very similar to TomoView in that we define the scan length, the scan resolution on the scan axis. For the frequency, we take all of the A scans on all beam sets. We have a zoom window that's enabled if I'm doing a 10,000 or 10 meter weld and I only want to visualize 1,000 millimeters at a time on the B scans and C scans. It's enabled here. This is where we inverse the encoder. There are shortcut keys in the lower left-hand side here to set the encoder to the preset position. Here, in this case, is a 0, and also to inverse the encoder here for scanning in the opposite direction. Once we're calibrated for the phased array, we can also check our encoder here. So it has a very simple calibrator. I'm going to position the scanner at a start position that's marked on my table. I'm going to hit start calibration, and this will reset the encoder to 0 here. I'm going to drive the encoder the fixed distance, and in this case 400 millimeters, and I'll stop right on the line as close as possible. Stop calibration at that position is going to tell me the new calculated resolution, and it will also tell me the percent error from my original resolution from the calculation. So in this case, we're less than 1% of an error rate. We can either take the new resolution here automatically or just accept it as being within tolerance, within tolerance, and move on. There's a series of specific data settings for the data here that include a default directory for where data will automatically be placed if the dialog box is not targeted to pop up. We have a root name that we can auto-populate in the name, and then these functions, similar to TomoView, again, will just determine if the inspection pops up a dialog box, automatically saves the file with a number counter on the end, and so forth. The software will know the size of the file that we're creating based on the configuration. In the data file, we save the acquisition version independent of the analysis version, and we also store the master serial number of the Focux PX, for which, again, up to 4 Focux PXs in a daisy chain together can be enabled, giving us up to a 32,512 pulsar configuration. The C scans and B scans available in WeldSight have also improved significantly, and they include a series of new displays previously not available in Olympus software. I'm going to switch to a clock inspection to demonstrate these. When on the clock inspection, the scan axis is configured in samples, and we will set the setup PRF and go to our inspection layout. So the first one is the one typical of OmniScan and TomoViews, the gate A amplitude. We start the inspection. The software transitions into a collection mode where various fields and forms are disabled and locked during the inspection. And this is an inspection typical of the OmniScan, where it will display all detections within the gate A sound path gate that we see here. A new inspection is now the weld gate amplitude. In the weld gate, this is based on the heat affected zone, or the HAZ, from the ES beam tool component overlay. Only detections within our gate will appear in the C-scan. And the third type is the merged gate A amplitude display, which gives us a real dynamic merge of the beam set S-scan data live. This is dependent on RAM and the size of the file. And this was something that we previously had to manage after the inspection in offline analysis. The various different types of displays, C-scans and B-scans, have no weight on the data file or the acquisition speed. They're only different ways of displaying data. So all of these layouts here can be pre-configured for the various different displays without any file size or PRF. Here's our weld gate. Here's our merged acquisition gate. And then, again, we have some pre-configured layouts for typical phased array and TOFT acquisitions. And these can be modified, customized, be moved up and down and applied as a file layer from the setup or data file. We're going to transition back to the PowerPoint again. This webinar is a part 1 for setup, overview, and basic acquisition. The next webinar will pick up where this one leaves off regarding in the software for advanced analysis functions and reporting. The WeldSight software, when used with the Focux PX, again, is a factory weld inspection specialist. It is most useful in environments where high repetition inspections of similar and sometimes different welds. In the wind tower calibration blocks that you see here, the operator would start his day by loading the scan plan, loading it into WeldSight, loading the TCG, and positioning the scanner on a series of side drilled holes and notches for his daily production. When he runs a dynamic cow scan of this plate, he can then update the weld bevel for each tower sections as they get thicker and thinner. This is a wind tower inspection that is designed to cover a range, in this case, of this plate is 12 millimeters, 25, 50, 12, 25, 37, 50, and 80 millimeters. So the entire range of this particular wind tower's factory is covered. Some of these have different side drilled holes on one side than the other. They have TOFT notches that allow us to quickly load a file and validate sensitivity, time of flight precision, and go right to work within about a 10 or 15 minute setup at the start of each shift. This is a typical S-scan, C-scan, TOFT display layout. The tower model overlays are all configured in advance as EBP files. We have a fast calibration workflow, and transition weld management is now available for the wind tower inspection. Another application is LNG tanks. There is enormous amount of construction happening worldwide regarding LNG processing facilities and the LNG tank construction, the giant tanks on land or spherical tanks on the ships. Olympus has a complete solution for the LNG tank inspection based around this Olympus quad probe that combines A27 DLA probes with A32 probes for a shear and refracted longitudinal S-scan inspection. training on the LNG app for a typical OmniScan inspector would be probably 1 to 2 days with a little practice, with an emphasis on use of the refracted longitudinal inspection. The LNG tanks are made up of a 9% nickel base material shells that are welded with an Inconel I625 weld. So only the DLA probes can penetrate the weld, but use of the shear wave pulse echo probes provide much more precision sizing on the weld bevel flaws. So having all 4 of the probes installed into a single connector defined by a single beam tool file make the setup, configuration, training, and day-to-day scanning of the LNG tanks very fast. A typical 2-man crew with this system could keep up with approximately 8 welders of various skill level working the same shift. The piping and vessels for the ASME compliance, when a ES beam tool file is configured as a pipe, the software will automatically enable the polar views that we see here for the merge and polar cursors for length sizing at various depths to account for the encoder on the outside of the pipe, distorting the length. So this is very useful and reduces the reject rate and gives us another analysis view. All of the configurations are enabled for the 3D modeling that we realize from the offsets in the beam tool when we created it, the UT data on 1 or more beam sets, a single-click 3D imaging that allows us to move and rotate this. Again, these are typical phased array and TOFT inspections, uniquely designed for the high repetition factory inspection. The last application we'll talk about today as an overview is the aerospace friction stir welds. Aerospace friction stir weld process uses an autonomous weld and creates a round pool that fuses aluminum together, typical of aircraft fuselage and rocket fuselages and other aerospace components. Because the aluminum uses the aluminum velocity requires us to generate the shear wave through a water wedge. So these wedges have a membrane that retain the water and slide directly on the smooth rocket or aircraft surface and provide a high resolution 10 megahertz inspection. These typically require multiple Focux PX daisy chained together for complete coverage in a single scan, which also includes a lateral 1D probe configuration. So if you have any particular application, especially if it's an LNG tank inspection that you are bidding on or evaluating, if you're a service company or manufacturer providing wind tower inspections internally or for a buyer, please contact your local Olympus sales rep, and we can take a 1-hour meeting and evaluate your application with you. In the follow-up email blast to this webinar, you'll have my contact information. Again, it's Chris Magruder, and you have my email address as well, and we'll evaluate those as they come in. We didn't allow much time for question and answers on this webinar. I saw that some were coming in the chat section. Again, in the email blast for this, we will answer all of the questions and send those links for the promotional material, the marketing movie, and some other WeldSight related materials in the follow-up email to this webinar. So I'd like to thank everybody for attending, and we'll look forward to seeing you again for our follow-up to this webinar for the advanced analysis part. Thank you.
Thank you, Chris.